In this video, we're going to talk about an important concept in thermochemistry called enthalpy. In this video, we're going to talk about an important concept in thermochemistry called enthalpy. Let's recall a couple of things from before. Endothermic reactions are reactions that absorb energy from the surroundings. Exothermic reactions are ones that release energy to the surroundings. If we were to draw an energy curve for an endothermic reaction, notice that the reactants are lower in chemical potential energy than the products, and the difference between those two is equal to the amount of energy absorbed. Exothermic reactions are ones that release heat to the surroundings, and their reactants are higher in chemical potential energy than products. The difference is the amount of energy released to the surroundings. Enthalpy, simply defined, is the heat content of a reaction system, how much heat energy it has. Now, we can't measure it directly. It's impossible to quantify the amount of heat content in a set of reacting chemicals. But what we can do is measure the difference in enthalpy before and after a change happens. So when we're studying thermochemistry, we're really studying changes in heat content or changes in enthalpy. A change in enthalpy can be calculated by taking the product enthalpy value minus the reactant enthalpy value. If you think of, and admittedly in equilibrium, we know that it's not always a progression from reactants directly to products, but sometimes it's helpful to link that together and say, okay, if my final state is the product state and my reactant state is the initial state, it's the same as saying final state minus initial state. Just in the back of your mind, remember, in equilibrium, you're not always going to end up with products. Okay, if it's an endothermic reaction, product enthalpies are greater than reactant enthalpies. So if you perform this subtraction, and by the way, all enthalpy values are positive. You can't have negative heat content. Okay, so a large positive number minus a smaller positive number gives you a change in enthalpy that's greater than 0. So for endothermic reactions, the delta H, the change in enthalpy, is positive. That means that heat energy is absorbed by the system. For exothermic reactions, as you can imagine, it's going to be just the opposite. Product enthalpies are less than reactant enthalpies. So when you perform this subtraction of a smaller positive number minus a larger positive number, the result is a negative value. Delta H is less than 0, or it's negative, and that expresses heat energy given off during the course of the reaction. One small thing, students, we're going to consider all reactions that we do to be done under constant pressure. Enthalpy is more than energy. It's energy plus the product of pressure times changes in volume. But if we have work done at constant pressure, then we can just say the change in enthalpy is equal to the heat energy. So we're going to go ahead and assume that for all cases in our class, at least. There is such a thing as the study of enthalpy changes under differing conditions, and that's a worthy pursuit, but it's beyond the scope of our course. When we talk about a reaction's standard change in enthalpy, notice the symbols, delta H, and then this little degree sign up at the top means when it's done under standard conditions. So 1 atmosphere of pressure, usually it's lab temperature, 25 degrees Celsius. And for everything that we consider, it's going to be under standard. Close enough to standard conditions that we can use the standard delta H. So standard enthalpy change is the amount of heat energy absorbed or released when the reaction is performed exactly as it's written in the balanced equation. What I mean by that, take a look at this balanced equation. 4 aluminum and 3 oxygen molecules react to form 2 aluminum oxides. The standard enthalpy change for that reaction is negative 3,352. First, note that that negative in front of the delta H tells me that this is going to be an exothermic reaction. We're releasing a good amount of energy. For every 4 moles of aluminum, for every 3 moles of oxygen, and for every 2 moles of aluminum oxide. This delta H value, negative 3,352, is the amount that we get energy released when exactly 4 moles of aluminum react. But students, you're not always going to have exactly 4 moles of aluminum. You might have 2.5 or 8.3 or 9.2 moles of aluminum reacting. You'll have a certain amount of aluminum that reacts according to the amount on hand. It's not going to be necessarily 4. The delta H, standard delta H also applies when exactly 3 moles of aluminum or 3 moles of oxygen or 2 moles of aluminum oxide are produced. So if it's not exactly those numbers, then we've got to do a little bit of calculating. Let me bring you to our Jamboard here. If we go consider this, consider the following balanced equation. It's the same one that we had considered just a moment ago. And we're going to calculate the enthalpy change that is associated with 1.3 moles of aluminum reacting in question A, and in question B, 5.8 moles of aluminum oxide. Let's do part A first. Start by writing down the amount of the chemical that the problem tells us. So if we've got 1.3 moles of aluminum present and reacting, and we want to figure out what's the energy change, how many kilojoules of energy are we going to get out of this reaction? I'm going to look at the coefficient in front of the aluminum and the standard enthalpy change. So I know that for aluminum, 4 moles reacting means that I'm going to get 3,352 kilojoules of energy out of it. I'm going to use that as a conversion factor. So we're going to write this information in the set of parentheses. And as we've done many times before, make sure that the quantity you put in the denominator is the thing that you want crossed out. The way we've written this is we've ensured that the unit moles of aluminum gets crossed out. Now, on your calculator, let's type in 1.3 times negative 3,352, and we'll divide that by 4. And I get negative 1,089. I'm going to round it there. 1,089. Part B. If we have 5.8 moles of aluminum oxide produced, let's start by writing down what the problem gives us. 5.8 moles of Al2O3. And then we'll write a conversion factor that will enable us to get to the number of kilojoules that are released. Now, this time we're going to look at the coefficient in front of aluminum oxide. So it's a 2. For every 2 moles of aluminum oxide that react, we'll get negative 3,352 kilojoules of energy. So this time our conversion factor is a little different. We're going to use this info to write into this set of parentheses. And just like before, make sure that the unit that goes in the denominator is the one that you want to cross out. Sorry, my digital handwriting's a bit messy here. Notice that the way we set this up, moles of Al2O3 crosses out. On your calculator, then, take what you have in the numerator, 5.8 times negative 3,352, and then divide that by 2. And I get negative 9,700, and I'm going to round to the nearest whole number here, 21, negative 9,721 kilojoules. And we could ask you about anything. We could say, hey, you've got, maybe we didn't do the oxygen yet. We could say, hey, 12.79 moles of oxygen react. How many kilojoules of energy are released? You could do the same thing. We would write a quick conversion factor. It's a one-step conversion. And then you would arrive at a number of kilojoules appropriate for that amount of the chemical. Good luck with the homework.